Good morning, Derek. I'm sorry.
Morning, Wyatt. Do you have any announcements to make?
Not really. You may go ahead.
All right, it's 8 p.m. here, so I might as well start.
Yes.
Can you allow me to screen share?
Yes, sir. Done.
Okay, so you may recall from yesterday that we were talking about Snell's law and ray parameter. And next, I want to talk about post-critical waves. These are rays that come in at angles of incidence beyond the critical angle. So J sub I, which is the angle of incidence, is greater than the critical angle. What this means is the reflected ray is phase shifted by an amount E, or by the amount theta equals tangent -1 mu2 R2 star over mu1 R1. And the transmitted ray is an evanescent ray, which means it decays exponentially with depth. All right, and we talked about this a little bit in our last lecture, but some relationships that we'll use that we've defined previously are R, which is the ratio of the horizontal wave number component with the vertical wave number component, the ray parameter P, which is 1 over the horizontal apparent velocity. And this is sine of the angle of incidence over the velocity in the top layer. And that also is equal to K sub x over omega. Eta, which is 1 over the vertical apparent velocity. And this will vary in each layer as opposed to P, which will be constant for a ray. And that's cosine of the angle of incidence over the velocity, which also equals K sub z over omega. So for C sub x, the apparent horizontal velocity, Snell's law tells us 1 over C sub x equals P. This is just by definition. And that equals sine of the angle of incidence 1 over the velocity in layer 1, which equals sine of the angle of incidence 2 over the velocity of layer 2. So we can rewrite Snell's law as sine of J1 times B2 equals sine of J2 times B1, or alternatively, sine of J1 equals B1, or sorry, beta 1 over beta 2 sine of J2. At the critical angle, sine of J2 equals 1. So that means that sine of the critical angle equals beta 1 over beta 2. And beta 2 equals the horizontal apparent velocity. When the angle of incidence is larger than the critical angle, J1 is greater than JC, and sine of J1 is greater than the sine of JC, just because J1 is greater than JC. That means beta 2 is greater than beta 1 over sine of J1, which is equal to the horizontal apparent velocity. So if J1 is greater than the critical angle, this implies that beta 2 is greater than the horizontal apparent velocity. And we'll see why this is relevant in a second. So let's consider what this means for a transmitted wave from the reflection transmitted wave. So here's the formula that we use for a transmitted SH wave. So we have an amplitude B prime times E to the I times these parameters. And there's no K sub Y because the ray is propagating in 2 dimensions. So it's propagating across and downward, but not propagating in and out of the screen. So we will recall that eta sub beta is the square root of 1 over beta squared minus p squared. And since r sub beta is by definition k sub z over k sub x, then eta equals k sub z over omega, which equals k sub x over omega times k sub z over k sub x, which equals p, since p equals k sub x over omega, k sub z over k sub x, which equals p times r sub b, which also can be written as r sub b over c sub x. So we have one formula for eta sub beta equals the square root of 1 over beta squared minus p squared, and another formula for beta or eta, and that's eta equals r sub beta over c sub x. We'll set them to be equal. And then we find with a little algebra that r sub 2 equals the square root of c sub x squared over beta 2 squared minus 1. Now, if the angle of incidence is greater than the critical angle, beta sub 2 is greater than c sub x. And that means that the value inside your square root sign is going to be negative and R2 will be imaginary. So when the angle of incidence is greater than the critical angle, R2 is imaginary. So let's pull out the I. So here I've just pulled out a -1, and now I'm taking the square root of -1 right here. And the square root of -1 is plus or minus I. Now, typically we say the square root of -1 is I, but also minus I is an equally valid root. So we have r sub 2 equals plus or minus I times the square root of 1 minus c sub x squared over beta sub 2 squared. So this means if the formula for the transmitted SH wave is given here by U sub y equals B sub prime e to the I omega t minus k sub xx minus k sub x r sub 2z, then if I take the I and multiply it by k sub x r sub 2 times z, that's an I times an imaginary value, which gives us a real value. So I times k sub x times r sub 2 is equal to plus or minus k sub x times the square root of 1 minus c sub x squared over beta sub 2 squared. And so this is a real value, and this explains how the amplitude diminishes or grows with distance from the z-axis, where the z-axis is the boundary between the two interfaces. So we can determine which value is realistic, the positive or negative value. And if we have a positive value, then this formula here will grow exponentially as we get away from the interface. And that would violate conservation of energy. So we can assume that the negative value is realistic and the positive value is not. So then we use the negative value. And that gives us a wave that decays. It's trapped at the interface. Here, I've called it a head wave, and it's got an amplitude that varies exponentially with depth from z equals 0 to some value. So we call this the head wave, and we can rewrite the formula for this transmitted head wave as b sub prime e times I omega t, e times minus I k sub xx times e sub minus I sub k sub x r sub 2z. And if j of the angle of incidence is less than the critical angle, the z component of this e sub minus I k sub x r sub 2z is sinusoidal. But if j sub I is greater than j sub c, then the z component is real because r sub 2 is imaginary. So you have an imaginary number times an imaginary number, creating a real component. And that gives us e to the minus k sub x times the square root of 1 minus c sub x squared over beta 2 squared. And this gives the depth dependence of the head wave. So this is called an evanescent inhomogeneous or head wave. A common one found in seismic records and something I use in my own research is P sub n, which is a P wave that travels along the MOHO, which is a seismic discontinuity marking the transition between the relatively low velocity crust and higher velocity mantle. So let's define our new exponential term as r sub 2 star, and that equals plus I times the square root of 1 minus c sub x squared over beta sub 2 squared. So r sub 2 star is just equal to minus I sub r2, or we could also call it r sub beta 2 star equals minus I sub r times beta 2. Just to emphasize that we're talking about the shear velocity in the second layer. And then the reflection coefficient, rather than being what I give for the pre-critical refraction, becomes this here, the post-critical refraction, and it's got an I term and the R star term in it. So let's consider what this means. So let's look at this complex number in its polar form. So for simplicity, let's just define A equals mu sub 1 R sub beta 1 and B equals mu sub 2 R sub beta 2 star. So the post-critical reflection coefficient is A minus I sub IB over A plus IB. And then we can use Euler's formula from complex numbers to say A plus IB equals e to the I theta. And then we can rewrite the numerator denominator of the post-critical reflection coefficient as R times e to the I theta over R times e to the negative I theta. So here we have in this plot the location of the numerator A sub IB and the denominator A minus IB. And we can calculate, just using simple trigonometry, the length of this vector R, and that's equal to the square root of A squared plus B squared. And the angle with respect to the real axis is going to be the arctangent of B over A. So we can say the reflection coefficient of a post-critical wave is e to the I2 theta. This has a magnitude of 1 and a phase shift of 2 theta, where theta equals the arctangent of mu sub 2 r sub 2 star over mu sub 1 r sub 1. So this phase shift depends on the angle of incidence, since r equals k sub z over k sub x, and k sub z varies with the angle. So here are some examples of a seismic waveform. Here's a 0 and 30-degree angle of incidence. You can see that these are identical. That's because these are not phase shifted. But as I go from 60 to 90 degrees, I get a phase shift, and that affects the shape of a seismic waveform. So for a post-critical incident ray, the reflected ray is phase shifted. The transmitted ray is trapped. So the transmitted ray has a depth dependence of minus k sub x times the square root of 1 minus c sub x squared over beta sub 2 squared. And beta sub 2 is larger than c sub x. So this here is a real square root. And the reflection coefficient is e to the I times 2 theta, where theta equals this arctangent formula. All right. So that finishes the lecture that from yesterday. And now I want to talk about surface waves, and we'll actually use evanescent waves to talk about surface waves. Whoops. All right. So surface waves are interesting for a number of reasons. They decrease in amplitude slower than body waves, and they also cause significant damage to large buildings that are relatively far away from the earthquake because they're at about the resonant frequency of these buildings. Longer period surface waves are sensitive to deeper earth structure, and shorter period surface waves are sensitive to shallower earth structure. So they are handy for inferring the depth distribution of velocity variations in the earth. There are 4 types of surface waves: Rayleigh waves, which are a combination of P and SV motion. So it will be seen on the radial channel. This is a channel of a seismogram that gets the horizontal shaking that is in the direction between the source, the earthquake, and the seismogram. The love wave is SH motion, and that's seen on the transverse channel. And that's the horizontal channel that is perpendicular to the radial channel. There's a Lamb wave, which is a type of Rayleigh wave that travels on a planar waveguide. One of my colleagues here just discovered them in glaciers. And then Stoneleigh waves, which are tube waves, which are important for borehole sensors, but for global tomography, they're not that significant. So we're going to ignore them. And we're just going to focus on Rayleigh waves and love waves. So a love wave has tangential or SH motion. A Rayleigh wave has PSV motion. So here's a animation of a Rayleigh wave. And particles will move retrograde near the surface, and actually at greater depths, the amplitude of their motion will be diminished, but they will eventually move in a prograde motion direction. So they will move forward rather than backwards. A love wave is side-to-side motion, and it's hard to see, but this animation is just reflecting side-to-side motion. And that is purely SH motion. So on a seismogram, if I look at the radial channel, again, that's the horizontal component of the seismometer that records the motion in the direction between the source and the receiver. We see a very faint P wave, and then we see an S wave come in, and then the larger amplitude is the Rayleigh wave. On the transverse channel, which will not be sensitive to the Rayleigh wave motion, but it will get the SH motion of the love wave, and we see the love wave come in. And you can see both the Rayleigh wave and the love wave, the longer wave periods come in, and then the shorter periods come in later. And this is due to an effect called dispersion, which we'll get to later today. And then finally, on the vertical channel, we also see the Rayleigh wave, because the Rayleigh wave is a combination of vertical motion and radial motion. So in this plot here at the bottom, I show the Rayleigh wave, it's retrograde motion in the source receiver direction and the vertical direction, whereas the love wave is motion in the transverse direction only. One of the cool things about Rayleigh waves is they can circle the Earth multiple times. So we talk about R1, which is the earthquake to the station direct path, R2, which is the earthquake to the station longest path around the backside of the Earth, R3, which is the earthquake to station path, but it's gone once around the Earth, and so on. So these are record sections that show the Rayleigh wave coming in. This is R1. So the x-axis here shows the distance. So 180 degrees is on the opposite side of the Earth from the earthquake, and 0 degrees is the location of the earthquake. And then we see later coming in is R2. And then at 3 hours, we see R3 and then R4. So R sub 3 has gone around the Earth once and is in the direction between the source and the receiver. And R sub 4 has gone around the backside of the Earth in more than once. So Rayleigh waves are a combination of trapped or evanescent P and SV waves that exist at the top of a half space. And we need that top of a half space to have a zero traction surface condition. And that is the condition that you get between an elastic medium and air. So let's consider the P and SV potential solutions to the wave equation. So we're going to write the P wave potential as phi and the S wave potential as psi. And since we're only going to talk about SV direction, we're not going to use psi as a vector. We're going to use it as a scalar. We will also use R again, which is the ratio of K sub Z to K sub X. And that equals C sub X times 1 over alpha squared minus P squared, or square root of that. We can stick the C sub X inside the square root to get this. And then we can note that P equals 1 over C sub X. So R sub alpha equals C sub X squared over alpha squared minus 1 square root. And we can do the same thing for R sub beta. The only difference is R sub beta is K sub Z sub beta. So K sub Z is going to be different for the P wave and the SV wave. So let's assume that R sub A and R sub B, or sorry, R sub alpha and R sub beta are imaginary. So analogous to how we dealt with evanescent waves. For this condition to hold, C sub x has to be less than beta, which is going to be less than alpha. In this case, R sub alpha is going to equal minus I times the square root of 1 minus C sub x squared over alpha squared. And R sub beta is going to be minus I times the square root of 1 minus C sub x squared over beta squared. We are talking about waves that travel near the surface of the Earth. Hence, at z sub equals 0, they must obey a free surface traction condition, where z is the vertical component. This implies that sigma sub xz equals sigma sub zz equals 0. And I'm just stating that. We haven't shown that, but that just comes from applying boundary conditions to the elastic medium free surface interface. We can calculate these from our isotropic relationship between stress and strain. And we want to get from potentials to displacement. To do this, we'll have to use a formula that we skipped. And in this, for a horizontal boundary, U sub x equals d sub phi dx minus d sub psi dz, and U sub z equals d sub phi dz minus d sub psi dx. This can be plugged into the equation that we had for stress. This equation right here, and set to 0 to get these formulas. Now what we're going to do is plug in the equations for U into the stress equations and evaluate them at z equals 0. And we will get the stress equals 0 equals 1 minus R sub beta squared times beta, sigma sub zz, which is also equal to 0, equals this formula here. And we will substitute in that and take into account that R sub alpha can be written as the square root of C sub x squared over alpha squared minus 1. And then we've rewritten our velocity relationships. So you might recall that alpha equals the square root of lambda plus 2 mu over rho. So we just took the square of both sides and multiplied it by the density to get this formula. And we did a similar thing to the shear velocity equation to get this formula here. This gives us two equations and two unknowns. And I'm not going to read them out, but here's the one equation, here's the other equation. And these equations have a non-trivial solution if the determinant is 0. The resulting equation is called the Rayleigh function. And it's equal to this formula here. And another way you might see the equation, this is just an equivalent formulation of it. And this is in Peter Scherer's book. Which is given here. So now let's simplify and solve these equations. So we'll first assume a Poisson solid, which is fairly accurate for the mantle, and that's the square of the p velocity divided by the square of the s wave velocity is 3. The determinant then becomes this value here. And there are 3 roots to this equation because it's an equation in c sub x squared. And only one satisfies the requirement that c sub x is less than beta, which is less than alpha. And when you solve for that root, you get c sub x equals 2 minus 2 over square root of 3 times beta, which is roughly 0.92 times beta. So now we can solve for the amplitudes of the potentials, which are A and B. So B equals A times 2 minus c sub x squared over beta squared, all that divided by 2 over r 2 times r sub beta. And this can be plugged back into the potentials and then solve for the displacements. So we have formulas for phi and psi in terms of A and B. And when we do that, we get u sub x and u sub z are equal to these equations here. And this has 2 properties. It has exponential decay with depth. So u sub z, which gives the deformation in as I go to greater and greater depths, is going to decay. We have negative values times the z value. U sub x also goes down with increasing depth. We have then exponential decay with depth, and we have retrograde motion near the surface, which is this backward directed motion. And then we have prograde motion at greater depths. Here I show u sub x and u sub z, where u sub x crosses this line or crosses the displacement equals 0 line. I go from retrograde motion to prograde motion. The phase velocity that gives the velocity that Rayleigh waves propagate at is sensitive to density, to p wave velocity and s wave velocity, and it varies with depth. So a 20-second wave period Rayleigh wave is shown by the blue line, and 133-second Rayleigh wave is shown by the green line. And what we can see is that the depth dependence increases with longer wave periods. It's particularly shown by the dependence of the phase velocity on the S wave velocity, where the 20-second Rayleigh wave is really sensitive to the lower crustal S wave velocity, where the 133-second wave is sensitive to the mantle velocity at roughly 200 kilometers depth. So at z equals 0 at the surface, we have this sort of particle motion, and that produces at t equals 0 motion that goes forward and then backwards. And so this is retrograde motion. And then at greater depths, we go from counterclockwise motion to clockwise motion. So in summary, Rayleigh waves have p as phi motion. We see them on the vertical and radial channels of seismograms. They need no special conditions to exist. Anywhere that there's a free surface, we can get Rayleigh waves. They are not inherently dispersive, which means that Rayleigh waves should, in a simple system, propagate at the same velocity regardless of their wave period. But in the Earth, because the S wave velocity in the Earth increases with depth, they are dispersive, which means that the longer period Rayleigh waves travel faster because they see higher velocities than the shorter period Rayleigh waves. So just to do a quick recap of what we've discussed. So we assume that R sub alpha and R sub beta are imaginary. We applied the free surface boundary condition that shear tractions are 0. We assumed isotropy, so the stresses could be converted to displacements. We wrote U sub x and U sub z in terms of the spatial derivatives of the P and SV potentials. This was plugged into the equation that we derived in step 3, and solving this gave us the Rayleigh function. Then we made an assumption, VPVS was assumed to be square root of 3, and plugging this into the Rayleigh function gave us a relationship between the potential amplitudes A and B. These relationships were plugged back into the equations of step 4 to get the real displacements U sub x and U sub z, which are shown here at the bottom of the slide. All right, so that was Rayleigh waves. I next want to talk about love waves. So to develop the concept of love waves, let's examine a lower velocity layer over an infinite and higher velocity half space. So we're going to talk about a low velocity layer such as the crust over a higher velocity layer such as the mantle. And we'll consider a harmonic SH wave. So rather than a P and SV wave, we'll think about an SH wave bouncing around in this layer. Since it's harmonic, which means it's a sine wave, there are multiple places on the wave path in which the phase is the same. So for instance, if this ray path bounces around on this layer, that the wavefront can have the same phase at A as it has at Q. So for a typical SH wave, B equals, or U equals B e to the I times omega t times k sub xx times k sub zz. So again, it's just propagating in the x and z directions, not in the y directions. And this is U sub y, because the displacement is going to be in and out of the screen. Now the phase is just given by the exponential term in the parentheses. So it's equal to omega t minus k sub xx minus k sub zz. Now we will rotate the spatial components into the direction of propagation of the ray. So we're going to convert k sub x and k sub z into k sub beta, and where the ray has an angle of incidence of j sub theta. So we can rewrite our formula in terms of U equals B times e to the I omega t minus k sub beta times d. And if we think about that, this should make sense because k, the wave number vector components, is the number of radians per unit length. And this gives the unit length. So this will be in terms of radians as well as omega t. And then what we will do, we will use these formulas. K sub z over k sub beta is equal to cosine of j. So the angle of incidence here. K sub beta is equal to k sub z over cosine of j, which equals omega over beta. And then the phase is just omega t minus k sub beta times d. So let's look at the phase difference between the wave at point A and point Q. If it is some multiple of 2 pi, then the waves constructively interfere. And we'll do this at time t equals 0. And we'll assume distance d equals 0 at A. So d equals 0 here, and then it goes larger and larger and larger until I get to Q. So the phase at A is omega t minus k sub beta times d. T is 0, d is 0. So the phase is 0 at A. The phase at Q is omega t minus k sub beta times d. Again, we're doing this at time equals 0. So this component, omega times 0 is 0. And the distance component is going to be k sub beta times the distance traveled. So this is d. And this is AB plus BQ. We also have to take into account an evanescent phase change. So a phase change will occur when the wave is reflected at the interface between the layer and the half space. So we're assuming something that's propagating at larger than the critical angle. And we get this phase change that we just derived. So there will be constructive interference if this formula here equals some multiple of 2 pi. We can do some trig substitutions for AB and BQ, and that gives us the equation shown up here. And since k sub z over k sub b equals cosine of j, which is the angle of incidence, and r sub beta equals k sub z over k sub x, then we can rewrite the formula as minus k sub x r sub beta times h plus the arctangent of mu2 r sub beta square r sub beta 2 star over mu1 r sub beta 1. That should say 1, not beta sub 1, 2. And that all has to equal n pi. So we've divided out the 2 here. We can take the tangent of both sides to get the equation here at the bottom. And we can note that the tangent of n pi equals 0. So our equation simplifies to be this here. Now we can rewrite this in terms of r sub beta equals the square root of c sub x squared over beta squared minus 1, and k sub x equals omega over c sub x. And that gives us this equation here. And this is only going to be real for c sub x, which is less than the shear velocity in the bottom layer, and it's more than the shear velocity in the top layer. All right, so now we have a transcendental equation, right? We have a tangent on the left side and a formula on the right side. So to evaluate this equation, we will define a new variable. I think this is a zeta. I forget what the name of this variable is, but I'll call it zeta. So zeta equals h over c sub x times the square root of c sub x squared over beta sub 1 squared minus 1. And then we can note that when c sub x equals beta sub 1, zeta equals 0. When c sub x equals beta sub 2, then zeta equals h times 1 over beta 1 squared minus 1 over beta 2 squared. And this is the range that c sub x, which produces real results. So this is the range over which c sub x is valid. So c sub x will vary between beta sub 1 and beta sub 2. So our equation now becomes tangent of omega times zeta equals this stuff here on the right. And now we can pursue a graphical solution to this. So we can note that the left-hand side of the equation, so the tangent term, is going to be 0 at zeta equals n pi over omega. and it's going to go to plus or minus infinity at zeta equals m pi over omega for m equals 1, 3, 5. So, and the right-hand side decays with 1 over zeta dependence. So we can plot the left-hand side as a bunch of tangent curves and the right-hand side as a 1 over zeta dependence, and look at the points where the two plots intersect, and that is where the equation is solved. All right, so if we look at here for a 5-second Rayleigh wave or love wave, the tangents are shown by the black lines, and then the right-hand side of the equation that decays as 1 over zeta is shown by the dashed line. And for a 5-second Rayleigh wave with a situation with these parameters, we have 3 solutions. And the lowest velocity solution is n equals 0. And then we have an n equals 1 solution and an n equals 2 solution. The lowest C sub x solution is called the fundamental mode, and higher values of C sub x are called higher modes or overtones. And we can see that the number of overtones that exist reduces as I go to longer and longer wave periods. So for a 10-second wave, we just have the n equals 0 and n equals 1. And for a 30-second wave, we just have n equals 0. So we can plot the apparent velocity of the love wave as a function of its wave period. And so we can see like the fundamental mode goes from 3.9 kilometers per second up to 4.3 kilometers per second as I get to a 30-second Rayleigh wave, or sorry, 30-second love wave, to at 100 seconds, we would get a 4.6 kilometers per second. So we see that this wave is inherently dispersive because the velocity that it sees is dependent on the wave period. We can also do an intuitive construction. So if we have multiple SH waves that bounce several times, eventually they will arrive closer and closer in time, and all these multiples will actually constructively interfere to create the love wave. So, and this occurs when there's a velocity gradient or there's a curved surface. So this is a method that you can create a love wave without just a simple layer over a infinite depth layer. All right. So that was surface waves. Does anyone have any questions?
Dr. Schutt.
Yes.
So the Cx is the horizontal velocity, you said. So is it P wave or S wave, or what type of velocity is that, the Cx?
It depends on what wave we're talking about. So for a love wave, it's the S wave horizontal velocity. For Rayleigh waves, since they're a combination of P and SV waves, it's going to be the apparent velocity of these both waves combined.
Okay, so does it have a physical meaning if it's combined?
Well, it's what you would observe at the surface. So if I had a line of seismometers in the direction that the surface wave was traveling, what I would observe is a peak traveling at a velocity that is given by C sub x.
Okay, thank you.
Any other questions?
Hello.
Hello, yes.
Yes, sir. In the love wave, the love wave is trapped in between the two velocity zones. Why we call a half space? And what is the half space?
Oh, a half space is a layer that goes to infinite depth, but it's truncated at the surface. So it's basically an infinitely thick layer. And that's a simple way of deriving the love wave. Although, like when I showed with the SSS multiples, we don't need a layer over a half space to derive a love wave. We can also get a love wave if I have a curved surface, such as the Earth, or velocity increasing with depth, which is also the Earth.
Okay, sir. Thank you.
Mm-hmm. Any other questions? All right, let's take a 10-minute break, and then I will talk about dispersion. So I will see you all in 10 minutes. All right, 10 minutes has passed, so I will get on with my lecture on dispersion. This is a fairly short lecture, so we will probably finish early.
Hey, Derek, I have a quick question. Hey, Derek, there are
Yes.
students. There are students who are asking about the homework. Like, where do they need to upload it? The homework.
Well, I'm sorry, what about the homework?
Where do they need to upload it? The homework.
Oh, they can send it to me via an email.
Okay. Thank you.
Yeah, that's actually a good point to recall that every 2 lectures will have a homework associated with it. It's voluntary, and the homework keys are also available on the OneDrive link. You're welcome to send me your homework or just grade it yourself, but the test at the end will be partially based off the homework. All right, dispersion is where wave velocities are dependent on the frequency or wavelength. So we can talk in terms of velocity is some function of wavelength, or omega equals some function of wave number. So the apparent velocity of love waves increase with wave period. So again, I'll show the example of the fundamental mode n equals 0 love wave. It goes from lower velocities to higher velocities with longer periods. This means that love waves are innately dispersive. So the wave equation tells us that the velocity of a phase is equal to omega over k. Dispersion tells us that omega is going to be a function of k. So for instance, with short period tsunami waves, omega equals the square root of g, which is gravitational acceleration times k. So that means velocity, which is omega over k, equals square root of g times k over k. Now, typically, we represent dispersion as some formula of omega and k is equal to 0. So we can rewrite this formula here as omega minus square root of g sub k equals 0. All right, so let's look at what dispersion means, and we'll derive phase and group velocities from this. So let's consider 2 waves with the same amplitude, but slightly different wavelengths. So we have one that is cosine of 2 pi over lambda 1 times x minus omega 1 times t. 2 pi over omega 1 is just k sub 1. So we can rewrite it as cosine k sub 1 x minus omega sub 1 t. And then we have another wave, which is a slightly different wavelength. And that can be written as cosine k sub 2 times x minus omega sub 2 times t. Since these waves have similar wavelengths, we can rewrite omega sub 1 as omega sub 0 plus d omega, and omega sub 2 as omega sub 0 minus d omega. And the same thing we can do with the k terms. So the total displacement of the 2 waves is just gotten by adding up the 2 waves. And so we have cosine of k sub 1 x minus omega sub 1 t plus cosine times k sub 2x minus omega sub 2t. And if we write that in terms of d sub k and d sub omega, we get this formula in the middle here. And then we can rearrange terms to get this formula here. And then we can simplify this with the trig identity of cosine of theta plus phi times cosine of theta minus phi equals 2 cosine theta cosine phi. So that gives us the formula of u, our displacement, equals 2 cosine times k sub x minus omega t times cosine dkx minus d omega t. So this is the product of two cosine waves. And if we have the top wave with omega 1 and k sub 1 up here, and the bottom wave here with omega 2 and k sub 2 here, and this has a slightly lower frequency, and we multiply them by each other, we get this formula of what we call a beating wave. So we have a long period variation and then short period variations. The first wave is called the carrier wave, and that is lambda equals 2 pi over k, or the frequency equals omega over 2 pi. And the second wave is the envelope wave, and that is lambda equals 2 pi over dk, and the frequency equals d omega over 2 pi. So the first wave is this, and the second wave is this long period wave here. So let's think about this in terms of velocity. So a wave with displacement u equals cosine ax minus bt has velocity b over a. So for our two interfering waves, we have the equation of the carrier wave with velocity omega over k. This is called the phase velocity. And for the envelope wave, we have velocity d omega over dk, and that's called the group velocity. In a dispersive wave, the phase velocity is different from the group velocity. So the phase velocity is shown by the red circle, and the group velocity is shown by the green circle. In a non-dispersive wave, the group velocity and the phase velocity are the same. So where there is dispersion, omega is going to be a function of wave number, or alternatively c, which is the velocity, is going to be a function of lambda. And in particular, c is the phase velocity. So in this case, when there is dispersion, the group and phase velocities are different. Using the chain rule, we can define the group velocity u is d omega dk, and omega is c times k. So that means u equals k dc dk plus c dk dk, or k dc dk plus c. So this gives us a relationship between the group velocity, capital U, and the phase velocity, little c. Now we can get the relationship between group and phase velocities in terms of wavelength by using k equals 2 pi over lambda along with the chain rule. So dc dk is equal to dc d lambda times d lambda dk just by the chain rule, and k equals 2 pi over lambda. So dc dk equals dc d lambda times minus 1 over k squared. And then we can say k dc dk plus c equals k dc d lambda times minus 1 over k squared plus c. And then we can multiply the outer k and the inner k to get dc d lambda times minus 1 over k plus c. And we can rewrite that as c minus 2 pi lambda dc d lambda, or big U phase velocity equals c minus lambda dc d lambda. If dc d lambda or dc dk is 0, again, the phase velocity and the group velocity will be the same, because this term will go to 0. So the group velocity is going to equal the phase velocity. But if dc d lambda, which equals dc dk, is finite, then the group velocity and the phase velocity will be different. So we can look at the group and phase velocities of love waves. So this is for a case with a 40-kilometer thick layer over a half space, and the density of the half space is 3.3 grams per cubic centimeter. The density of the layer is 2.8 grams per cubic centimeter. The velocity in the half space is 4.6 kilometers per second, and the velocity in the layer is 3.9 kilometers per second. So the group velocity here is less than the phase velocity. So in Earth, typically dc d lambda is going to be greater than 0. So c will typically be greater than u. So some real examples of love waves. If I filter love waves at these frequencies, 14.5, 19, 28, 51, and 109 seconds, we can see the envelope and then the short period oscillations within the envelope. We can measure the velocity of the envelope function as a function of ray path to derive the velocity versus depth along the ray path. So here's an example, it's a famous example from Forsyth, where they measured there's an earthquake right here, and they measured the velocity along a mid-ocean ridge, the Walvis Ridge, and then the velocity off the ridge. They found the off-ridge velocity, the group velocity followed this top plot here, and the on-ridge velocity followed this bottom plot. And you can convert the group velocity to S-wave velocity as a function of depth. And they found this here. And what they found is that the off-ridge velocity was lower, particularly above 50 kilometers depth. So, and all that is doing a bandpass filter on the love waves and calculating the position of each envelope. And that gives you the time it takes, which gives you the group velocity. Another way to do things is to look in the frequency domain. So we would do a Fourier transform, and we'd plot f of x of t in terms of f of omega t, where omega is 2 pi times the frequency. So a famous plot by Nishimura and Forsyth, where they looked at earthquakes along different ages of oceanic plate. So 0 to 4 million years, 4 to 20 million years, and so on. And they found these are phase velocities now. And they found phase velocities as a function of wave period. They all went up with wave period, but definitely the younger plate was lower velocity than the older plate. And if you convert that to S-wave velocity, here characterized as beta, as a function of depth, you get the younger plate has this low velocity feature, and then you get the older plate. progressively older plates have higher and higher velocities until you get down to 150 kilometers depth, which is the, I'd say that's the top of the asthenosphere for the oldest plate. We can also do seismic tomography, where we calculate the phase velocity at different wave periods in different paths. So this is for the United States. This plot actually didn't show up too well, but this shows the track of the Yellowstone hotspot, if anyone's heard of that. So the red and orange show low phase velocities, and then the blue shows higher phase velocities. And then I can convert that, you can convert that to S-wave velocity as a function of depth. So another type of dispersive wave is tsunamis. Tsunamis are non-dispersive when the wavelength is significantly longer than the ocean depth. So the phase velocity is going to be the square root of g times depth, regardless of the wavelength. For the case when the wavelength is longer than the ocean depth, for shorter wavelength waves, dispersion does occur, and the phase velocity equals the square root of lambda times g over 2 pi. So water wave group and phase velocities do not match, especially at shorter wave periods. Here we see the phase velocity and group velocity for shorter periods, and the phase velocity is more than the group velocity. This 2 kilometers, 4 kilometers, and 6 kilometers gives the depth of the oceanic floor. And the left plot here shows an example. This shows a tidal gauge. So it's not very smooth reading, but it does show the longer period waves coming in first, followed by shorter period waves. And the ray paths are also sensitive to ocean depth because the phase velocity is sensitive to ocean depth. And so tsunamis can get focused or defocused depending on the topography of the oceanic floor. And that's all I had to say about dispersion. So are there any questions on dispersion or surface waves? Or are there any questions on anything so far that we've covered?
Yes, sir.
Go ahead.
So, as compared to overbid high velocity. What is the reason behind?
Sorry, you're not coming through.
I am audible, sir.
Can you say that again?
Let's have lower velocity to low have higher velocity. What is the reason behind it?
I'm sorry, I can't hear you. The connection is bad. Can you type your question in the chat? Sorry, I didn't get that.
Dr. Schutt, I had a suggestion.
Yeah.
So since there are too many variables and too many symbols, would it be possible for you to provide us a comprehensive list of the meanings of all those symbols, because there are too many symbols to remember?
There are, aren't there? Yes, I'll try and put something together. I'll hopefully be able to finish by tomorrow. And normally in class, we would work through each symbol and we'd calculate the values of each symbol. But because this class is a bit accelerated, we won't have too much opportunity to do that. But I think we will have some time, as I'm discovering this lecture being done early. So yeah, I'll put something together and I'll do a talk on it.
Okay, thank
That's
you.
a good point. Yeah.
Sir,
Sometimes this thing means different things in two different lectures. So I think it would be better for example, phi symbol has two meanings, right? One is a P wave potential, another one is the phase, right? So similarly, so if you could make one lecture specific or maybe chapter specific, because in the next chapter, the same symbol might mean something else. So yeah.
Yeah. So unfortunately, I'm following the convention of most seismologists. So most seismologists use phi for the S wave potential and psi for, or phi for the P wave potential and psi for the S wave potential. But we also use phi for angles.
Exactly.
So yeah, I don't really know what to do there because I want you to be able to read seismology texts and be able to interpret the meaning of the variables. And I think using the conventional usage of them will help there. So I'll try and be more clear when I define different variables. And to be honest, we're mostly done with the sort of heavy definitions of variables.
Okay, thank you.
Yep.
hello, sir. Sir, why phase velocity of younger plate is lower? Sir, is it due to the elastic parameters?
Sorry, can you repeat yourself? I didn't quite hear you.
Yes, sir. So can you hear me?
Yes, I can now.
Yes, sir. Sir, in graph you have shown that younger plates has lower phase velocity and the older plates has a higher phase velocity. So, sir, is it due to the change in elastic parameters with age or something else? The reason behind it?
So I'm sorry, I didn't quite understand what you said. There's a higher velocity.
Sir, I am saying, sir, in a graph, the younger plates has lower phase velocity in a dispersion graph with the age. You have shown
Oh,
at on slide 21. Yes. So,
so
sir, the reason behind it is it due to the elastic parameters, change in elastic parameters with age, or something else?
that is due to the change in temperature. And the change in temperature affects the shear and bulk modulus. It reduces them. And that causes a lowering of velocities. So the
Okay, sir.
youngest plate is hotter than the older and colder plates.
Okay, sir. Thanks.
Sir, uh, as we have seen in the slide, so at certain points, the retrograde motion of the relay wave converts into the prograde motion. So, what condition at that point prevails so that this phenomena is observed?
Can you say that again, please?
So, at some point, the retrograde motion of the relay wave is converted into the prograde motion. Okay,
Yeah.
as we have seen in one slide. So, at certain depth, so what condition prevails at that point?
Oh,
So, is there some? Yeah.
it's just that the formula for U sub x goes from positive to negative. And so that boundary is where U sub x is equal to 0 between retrograde and prograde motion. It doesn't mean anything physically, like it doesn't mean anything about the media through which the wave is traveling. It's just a characteristic of the Rayleigh wave.
Okay. Thank you, sir.
Sir, so since there was a lot of material covered, which reference book can we refer to get more understanding and insights into these?
Yes, I can put a PDF of Stein and Weiss session, which is the book that I teach out of, online. And we are doing chapter 2 right now. And then towards the end of this class, we will do bits of chapter 3.
Yes, sure. Could you please post it by today evening or something?
Yeah, I will do it today or tomorrow.
Okay, sir. Thank you.
Yeah. Any other questions? Okay.
I would suggest to all the participants, if there is any issue regarding the question that the question is not being listened or there is some network issue, please post your question in the chat box. That will make our things little simpler.
Yeah, occasionally my connection is bad and I can't quite hear people. All right, so in tomorrow morning's lecture, I will start with a review of the different parameters that we've used. And I will also address any questions that you have on the homework. And then I will go into the main lecture. Any comments or questions? Okay, great. Let's finish up here then. And I will see you tomorrow night.
Yes.
Or no, tonight, sorry.
Yeah,
I can't get the time change right.
That's fine. That's fine. Okay. So thank you so much, Derek. We will meet in the evening. Thank you.
All right, I'll see you all.
See you, sir.
Thank you, sir.
Thank you, sir.